Hi there everybody, how you doing? Hope you're all well and your families are well and you're coping with this lockdown. I know you'll probably still be working, but it's been bizarre this Groundhog Day again and again and again. But hopefully it'll not be too long before we can have that big party when we're all free. Right, so this module was going to be kind of a hands-on practical kind of thing, and obviously that's going to be quite difficult to do considering the circumstances. So what I'm going to do is, well, what we were supposed to be looking at was an electrical testing circuits and things, and then we were going to do some sort of mechanical testing. And what I plan to do, mechanical can mean flow of fluid as well. And in the lab at the college there's what they call a Venturi flow machine, and I was going to have a look at that and we were going to go through that, but obviously that's going to be impossible now. So what I'm going to do is I'm going to look at flow and I'll have to go through some of the theory with you, and after that I was going to look at an electromechanical system such as a motor, so we could check how much force it's creating or how much torque or something, and how much electrical energy was needed for that, like how much voltage and current, and we were going to compare them. And I'll probably be able to do a bit more of that because I managed to do a little smash and grab before the college closed down, and I got an oscilloscope and stuff. I got a function generator, and what that means is it creates electrical pulses and stuff that we can look at on the oscilloscope, and I'll be able to make up little videos of me checking things out and testing stuff. It's not ideal, but it's probably the best we can do under the circumstances. So in this first lecture I'm going to look at ammeters and voltmeters and look at the kind of how they work using a thing called a galvanometer, and then we'll look at the digital multimeter. I tried to get an analog one but I couldn't find one on the last day actually. But we'll have a look at the digital multimeter and look at how you set it to measure different currents and voltages and what sort of range you set it at. And initially though I'm going to look at, for instance, when you twist the digital multimeter to different settings, that attaches it to different sizes of resistance in the circuit, and that changes the characteristics, because like in the analog ones where you've got the old fashioned kind of galvanometer type thing, you could only get a certain amount of current could go through that without it burning it out. So what you needed to do was muck about with the resistances to try and ensure that what you're measuring was only a small percentage of what's actually going through the circuit. And obviously that makes it a lot more accurate as well, and it protects the galvanometer. And if you look at an ammeter first, in other words, look at how to measure the current in a circuit. From that you can actually use that and turn it into a voltmeter. And as I say, I'll go through the kind of theory. I don't really expect you to completely or 100% understand it, but what you'll be left with is a couple of equations at the end of it, and they're very simple. So I would expect you to be able to plug the values into the equations to work out what size of resistor we need, depending on the circuit that you're measuring or what you want to measure. Yeah. So, and I know this is difficult to see at times. It's hard to see here, But what I've got this other wee camera doodah thing here, and I can switch backwards and forwards. The only thing is I have to switch this off and restart it again, which is a bit of a pain. But so if you kind of bear with me, and we'll go through ammeters and voltmeters in the next wee while. We'll look at a couple of examples of how to work out what you call your shunt resistors, and then we will look at the settings of the digital multimeter and what you need to set it at to measure a particular circuit. And then we'll have a look at what an oscilloscope does and how that measures frequency and voltage and that kind of thing. And what I'm thinking is, if I make kind of like 6 kind of lectures over the next few weeks, and out of that I'll do some sort of tutorials for that. And I'll send you tutorials. If you send them back to me, I can use that as evidence to see how you've progressed in the course. Okay, good stuff.
So I'm quickly going to look at a galvanometer. I hope you can see that. I'm going to do the other kind of calculations on a bit of paper on your camera there, as I says. So a galvanometer is a device which kind of looks like that, and it's got a coil round it and around a magnet, and it's got a wee scale thing. It's got a wee pin or needle, and you have a scale, and if you put an electrical current through that, that'll make it move because of Faraday's electromagnetic induction. Right. Now, depending on how much current goes through that depends how far it will move from left to right. Usually what happens is it will start in the middle, and then if you put a current one way, it will go that way, or if you put a current the opposite way, the needle will move the other way. And what they call this is, from say this thing had a maximum current of say 200 milliamps, microamps, microamps. This would go from 0 to plus 200, and if you went the other way, it would go from 0 to minus 200. That's basically kind of how it works in a general sense, and it's how you wire this up and how you regulate the current that goes through this coil here. It determines how it's going to work and whether it's going to work well. So now, say you are wanting to measure a current in a circuit, say you had a wee resistor there, and you're wanting to measure the current in this circuit. You would attach your ammeter in series in the circuit. Now, the ammeter is going to look kind of like this. So the ammeter, see, you've got this wire coming in like that. The ammeter is kind of set up in a kind of parallel way, where you have this resistance here. I'm going to put a small Rg to indicate it's part of the galvanometer. It's the internal resistance of the galvanometer, they call it. There's the galvanometer, and you have what we call a shunt resistor. This is going to crawl across here. Now, I'll call that R, S, and you have an incoming current here. Now this current is going to split up. Some of it's going to go this way and some of it's going to go this way. And what we're wanting, we want as little of this current to go up here as possible, because the more current that goes up here, the more the less accurate it's going to be, because we are trying to measure the current between here and here. So what we're wanting to do is to kind of limit the amount that goes up here, and we're going to try and kind of make some sort of ratio here that allows us to measure. So for instance, say you had 50 amps going along here, and you set this a ratio of kind of roughly 50:1. So if you had 1 amp coming along here, the galvanometer, you would set these resistances, so you'd be able to say, well, there's 1 amp through here, but I know that's actually equal to 50 amps. Or if, say, that was a half an amp, you know that half an amp is going to be 25 amps. It's basically, when you're trying to work out to use your galvanometer, you have to relate it to what you're actually wanting to measure, and that's where this resistor comes in here. We have to change this resistor to allow us to measure the different currents. And this is the thing, see, when you use a digital multimeter and you switch it between different settings, what you're doing is you're just changing this resistor, and that allows us to read different currents at different scales. Now, so let's see, so we'll have a current that comes through the resistance, and we're going to have this current here is going to be current G, we'll call that. So this is a current that goes through the resistor, and this is a current that goes along through the galvanometer. Right, and what we are wanting to think about here, right, say in a parallel circuit, say that was A and B, the voltage from there to there is going to be the same as the voltage from here to here, because that is a parallel circuit. We have looked at parallel circuits before, so this should be familiar to you. Now, your voltage then is going to be equal to the resistance here times this current R minus the current G. You see that? So the current going through here times this resistance is going to be equal to the voltage that's over here. Now the voltage over here, which is going to be the same as it, is going to be the resistance of the galvanometer times the current going through the galvanometer. I hope that makes sense. So the current that's coming in here, this I, is getting split up, and IR is coming along here, and IG is going along there, and then they recombine again here, and you get the same volt current here as you get here. So what we generally want to work out is this RS. So RS is going to equal RG times IG, so resistance of the galvanometer times the current of the galvanometer, divided by the current of the resistance minus the current going through the galvanometer. So, and that gives us the ratio of how we work out the size of this resistor. Let's have a little, I'll do a little example here. Can you see that properly? Well, that's moved a little bit. Hope you can see that. Right. So say for instance, we had a galvanometer that has a full scale deflection of 200 microamps. Right, and this is the bit, see, like your scale, this is where it's went from 0 to its maximum on the, see, the positive side. So that's 0 and that's 200. And if it was wired the other way around, it would be like minus 200. You call that the polarity, right? And say the internal resistance was 10 ohms, and we wanted to measure, this is what we want to measure, the IR, the current going through there, we want to measure between 0 to 10 amps. Now we can work this out then. This shunt resistor is going to equal the resistance of the galvanometer, which is 10, times the current, the maximum current that can go through the galvanometer, which is 200 times 10 to the minus 6, and that's your, so that's your IG, that's your RG, it's supposed to be a G there, and then divided that by 10 amps, this is that part, the maximum there, minus 200 times 10 to the minus 6. That is going to make a lot of difference to that. That's going to be just about the same, to be honest. So this actually works out at 0.002 ohms divided by 9.9998, which equals 2 times 10 to the minus 4 ohms. That's tiny. It's very low. So what that means is this current coming along here, this is 10 ohms, which is small. This is, what's that? That's like 0.0002 ohms. It's absolutely tiny. In fact, it's 0.0002 ohms. So that's tiny. So what that means is the current that's coming along here sees 10 ohms here, and it sees 0.0002 ohms here. So this is a much easier path to travel. So most of the current is going to come down there, and this is just going to take a little sample of that current, and it can measure it from that. And because we've set the resistances in this particular ratio, when it measures this tiny wee current there, it can multiply that up to whatever we're wanting to measure, which was this 10 amps. Okay, that's the general explanation of how an ammeter works. As I say, I wouldn't expect you to regurgitate this, but if you've got this equation though, I'll set you a couple of wee tasks to work out the shunt resistor. Good stuff. Right, I hope you've got that. I'll put a couple of examples up on a wee tutorial for you. And I'm going to look at now is turning this galvanometer into a voltmeter. And so just bear with me a second. Right, now what we've got here again is a circuit. You see that? It's a bit low maybe. A circuit which has a resistance. Pull this down a little bit. And we'll go back to there. Now we want to measure now this is a voltmeter. And now we want to measure the voltage across this resistor here. Now, what we say, we attached a galvanometer across here with its wee internal resistance Rg. Now if we attached it like that, that's got a very small resistance, which means the current coming to meet, say that was like 1000 ohms, and say that was like 10 ohms, the current's all going to try and travel through there. And not only would that give you a bad reading, it would blow your galvanometer. So to give us accuracy and protect our equipment, we have to actually reduce the current coming in here. So what we need to do then is add another resistor here. Again, a shunt resistor we call it. And that's not very clear, I suppose, but what I'm doing there is, wait a wee second. What we've got here is a resistor there, and that's going to be a RS, remember that's your RG, it's hard to see, I'll put that down there, RG. Now, what's going to happen is you're going to get a current that's going to go up here. We'll call that IG. Right. Now, what you're kind of left with, say it kind of looks like that. You can still see that. And you're measuring the voltage across here, and this is where your resistor is. And you have, it's looking like that, your RS plus your galvanometer. It looks like that. Right, remember that's got Rg, resistance, internal resistance of the galvanometer. What you've got coming up here is Ig. Now again, that's a parallel circuit, so the voltage here is going to be the same as the voltage across here, which is, remember, V equals IR, so the voltage across here is going to equal Ig times the resistance of this shunt resistor plus resistance of the galvanometer. Looks like that. Now if we want to, we can kind of rearrange this then. We can say Ig equals V over Rs plus Rg. Right, now, and then what we can do, if we want to and then to make it a little bit easier, what I would do is say Rs plus Rg, because that's multiplied by Ig. If I put that across the other side, that will be that, like that. You see what I'm doing there? If you see that? If you divide this by Ig and divide the other side by Ig, they cancel, and you're left with R shunt plus Rg equals V over Ig, and Rs equals V over Ig minus Rg. So let's have a wee example. Say you wanted, say the full scale deflection Ig, which FSD's full scale deflection was 20 microamps, and you wanted to measure 100 volts, and say for instance Rg equals 50 ohms, and we can just plug that into that equation then, and what we're going to get is Rs equals V 500 divided by 20 times 10 to the minus 6 minus 50. That is going to equal 4.999950 ohms, or 5 mega ohms. In other words, it's massive. And you can see, right, see, if you want to measure the voltage across there, if you make that a massive across here, if you make that a massive resistance, that current is going to be tiny. And because you've used this equation and set the resistances, this will mean that your full scale deflection of this 220 microamps has been sort of calibrated, so you can measure 100 volts from that. And remember, if you've got a resistance here, to measure the voltage, you are measuring the current and the resistance that's going across here. So that's how you can use an ammeter or a current measuring device to tell you what the voltage is over an unknown voltage is over a resistance. Good stuff. I hope that's making sense. I'll do another couple of examples for you in a wee while, but what I'm going to do now is have a quick look at a digital multimeter and kind of like how it works. Right, we were talking about kind of shunt resistors for ammeters and voltmeters, and the beauty of a digital multimeter, it's all kind of calibrated and set for different levels that are commonly measured, and you have your kind of galvanometer. Anyway, right, we'll forget about that. What you have is, say, your kind of mechanism, and you will have, oops, it's not a very good drawing. You have all these different kind of resistance setups, and when you twist your dial, it twists and it'll attach to these different resistances here, which will change the characteristics of your multimeter. We'll have a quick look at one just now. So, wait a second. So looking at this here, you can see that's what I was talking about, where you can set this to your different settings. That there, I'll put this down a little bit, that's a bit better, you can see a bit closer. You can see there that little line with the wee dotted line underneath, that's a DC voltage, which means that it just travels in one direction, direct current. Now if you look at this one, it's got a wee kind of wave next to it. That's for measuring alternating current. That's supposed to simulate a kind of a sine wave, and that's when it travels backwards and forwards. And this A here is when we're measuring current and this again is AC current, as it says there. You can see that. And again, this is DC currents. And up here is actually what this is for, is testing resistance. We'll have a wee look at that in the next lecture. I don't want to do too much just now. That's a little bit more complicated. And so, I mean, looking at this, say you wanted to measure 200 millivolts, up to 200 millivolts. So that means in this scale here, this will measure up to 200 millivolts. Did I say ohms here? Millivolts. Here, this will measure up to 2 volts, and 20 volts, 200, up to 1000, and so on. And so whatever kind of voltage range, if you're wanting to measure between 1 and half a volt, or from 0 to 1 volts, you'd probably pick that one in AC. Say you wanted to pick, you're measuring 10 to 15 volts in DC, you pick that one. And your currents, depending on what size of currents as well, you have to change this here to this current, oops, sorry, this here to the current, depending on what sort of size, because this is it's got sort of protection in it to stop the circuit getting blown. So you can measure up this, you can measure up to 2 amps, and this one up to 10 amps for this particular multimeter. You can see that there as well, but it gives you the maximum of 10. Any more than that, I can blow this. 10 amps is quite a lot actually, and so you have to be careful of that, because if you blow the fuses in these, you have to take them apart and change them. It's a pain in the backside. You have other functions as well. This one's for testing transistors, and you pop them into there, and that tells you the characteristics of your transformer. And this is your continuity. This tells you if the circuit is continuous, isn't any breaks in the circuit. Right, it's quite straightforward. I'm going to give you a wee tutorial on that as well. It's very simple, and I'll just ask you what settings you would put the multimeter at to measure particular circuits, etc. So let's see. Right, so I'm going to send you a tutorial looking at how to calculate the shunt resistor for ammeter and voltmeter, and then I'll send you a wee tutorial on what where was it? What settings to set the digital multimeter at. And what I'm going to do as well is I'm going to give you a couple of circuits, and what I'm going to do is I'll get you to work out what the voltages should be at certain points and currents, and I want you in the tutorial to tell me what you think the current should be and the voltage, and then what I'll do is I'll kind of video myself measuring them, and we'll see what we get. Okay. I think that's just enough for now. And we will look at oscilloscopes. Well, you know what, we could have a quick think about oscilloscopes just now actually. Oscilloscopes, very versatile instruments. show you graphically exactly what's going on in a circuit. It's especially handy with AC circuits, alternating circuits. There's certain limitations to when you get analog oscilloscopes and digital oscilloscopes, and there's differences between them. Obviously analogs are older ones, but that still has certain properties that modern digital ones can't use, and you have problems with both. Generally a digital multimeters, oscilloscopes does the job, and analog ones are very rarely used nowadays, although in some situations they have to get used. And also what we're going to look at is problems incurred with meters as well, multimeters and analog meters. And I'm going to do another wee lecture on the problems with meters and how they can affect your results. Now oscilloscopes, a cathode ray oscilloscope is what I call a cathode ray oscilloscope, or cathode ray gun. Can you see that there? And it has little plates here, and it fires off electrons, and dependent on the voltages on these plates here, it makes the electron move, and that is the electron beam move, and that is proportional to the amount of current or voltage that you're measuring that's getting applied to the oscilloscope. And this kind of gives you a reading on your screen, and it's got a thing called graticules. That's the word of the day, and basically it's just like a little grid thing like that. It's not very well drawn, but and these allow you to visually inspect what's going on. The thing about a digital one, the digital samples it tells you exactly what it is, so there's less confusion and less error of judgment than the old analog ones. So the analog ones, you had to kind of look at your grid and kind of judge it, which isn't as accurate. And so say, and also what you would get, this grid here, up this side is the voltage, or like the magnitude of the voltage, and along here is what they call the time base. Right, and say you had a signal that was coming in like that, and say that to one, say to do one full cycle from there to there, you used 1, 2, 3, 4, 5, 6, say you used 6 columns or 6 gaps, and each one of these gaps was 0.1 second. That means for the whole cycle it would be 0.6 seconds, which would be, if it takes 0.6 seconds to do one cycle, in one second, then you'd probably have about 1.8 cycles. So you can work out the frequency of your signal by looking at how many spaces it uses in the time base. And then if you want to check how big or the magnitude of the voltage, see that's the middle line, this is like 0 volts, you would just measure the height here and measure how many boxes it takes up, and that will tell you the voltage to here. You have to remember with an AC current or AC voltage, you have like see your 240 volts you get from the socket, that's actually just this part of it. This is 0, and it goes 240 up to 240 volts in the first half of the cycle, then it goes down to minus 240 volts. So what they call your actual peak to peak voltage is actually 480 volts. I don't know if you knew that actually. So what you're doing is your voltage is going from 0 to 240, back down to 0, and down to minus 240, then back up to 0. And you can measure that with an oscilloscope. It's really handy. And the digital ones have like, and the analog ones as well, but you may have two channels in it. So you can attach, you can show, so what that means is you can show two different values on the same screen. So you can maybe look at the oscilloscope. We'll do this for the electromechanical one actually. We'll have a trace showing your voltage, and we'll have another trace showing the current, which from that you can work out the power of the motor or whatever it is you're checking. And from that, what I could do is I'm going to set up a little motor, and I'm going to get it to pull a weight up, and then we're going to work out, say like the acceleration of it, and work out what force it's creating, work out how much energy that would be needed, or how much power, and then relate that back to what we get from the oscilloscope, and see what the differences are. We will lose something. If we put 10 amps and 10 volts, you should get like 100 watts out of it. What you'll find is you'll maybe only get 92 or 93 or something like that, maybe less, depending. And we could adjust the weight so it's maybe got more friction and make it harder for it to pull up, and that means there'll be even more losses. And efficiency nowadays is one of the main things that we have to look at in engineering. Conservation of energy. Not just because we want to save the planet and all that. What I mean is if you got like a complex instrument, say like a mobile phone, it's a complex electrical instrument and it needs quite a bit of power. Now if we make that more efficient, that means our battery's going to last longer. So, which is fair enough if you're out camping or something like that, but more importantly, if you're going to Mars and you're using complex electronic equipment, you want that to be as efficient as possible. Not so you'll be able to speak to your pal the next day if it hasn't ran out. It's so you can get to Mars safely and still have power to communicate, that sort of thing. And that's just one small aspect. There's all sorts of different aspects why we want to be efficient with our electricity, of course. Now, and obviously we will look into the kind of errors as well you get from analog and digital oscilloscopes. So from this lecture, if you can think about the ammeter, the galvanometer, the ammeter, the multimeter, and the kind of oscilloscope. What I'll do is I'm going to send you a tutorial with a couple of questions on the ammeter, a couple of questions on the multimeter, sorry, the voltmeter. I'm going to ask you how you set your digital multimeter to measure a set value, and then I'm going to send you a couple of circuits on the tutorial as well. I want you to tell me what the voltage and the current should be, and what I'll do is I'll make another video of me testing these things and we'll see how you got on. As I say, I'm hoping to do like 6 all in all, sort of 2 lectures for the 3 different parts of it, but that will still leave us another 3 weeks because it's week 9. Sorry, it's week like 4 as such. We've got 9 weeks left. So week 4, 5, 6, 7, 8, 9, and that will still leave us 3 weeks. We're doing a couple of bits and bobs or tying up any loose ends. I've still got a couple of reports in from a couple of people. I've even got 1 or 2 things from comms actually. and I'll need to have these things in because I need to have evidence that you've at least done something, anyway, put it that way. But so that's it, I think, just now. And this won't be like, I'll be putting another video up maybe before the end of this week if I can. And as I say, I was going to do 6 main kind of lecture videos, but I will be putting up, like for the tutorial thing, I'll be putting up extra wee videos, just wee 5-10 minute ones. So it'll be more than 6 videos, but it's 6 main kind of lectures. Okay, right, take it easy everybody, bye.